In the last couple of videos, we reviewed the energy balance, which is personally one of my favorite equations. And for as awesome as it is, it has a fatal flaw that it doesn't tell you the whole story. So consider this alternative example. If we have steam at 550 C and 30 bar, and it enters a steady state adiabatic turbine. If the exit stream is a saturated liquid water at 1 bar, how much work per kilogram is produced? So go ahead and pause the video, see if you can draw yourself a process flow diagram and see if you can actually solve this problem. I think that you should be able to solve this problem now with the information that you have by using the energy balance. This is what your process flow diagram should look like. I have an adiabatic turbine, so I also need to go ahead and label that Q is equal to 0 in this case. I've got a fully labeled couple of streams, so I've got M1 steam coming in, 30 bar, 550 C. Exiting stream is saturated water at 1 bar. Although I don't know the temperature, because I specified it was saturated water, you could actually look that up. But in this case, you don't need to do that. You just need to know that it's saturated water in order to solve the energy balance. So once again, the mass balance is trivial in this case. I could say that M1 must be equal to negative M2. And remember, it's negative because of the Sandler notation. He loves to have outlet streams as negative. So don't read too much into the fact that you can't have a negative flow rate. Again, it just means it's coming out of the system. It takes some getting used to, but it can make things go a little bit smoother. All right, and the energy balance in this case simplifies to, so it's steady state, so I've got 0 for the time derivative term, so du dt is 0, equals energy in minus energy out. So it's going to be m1 h hat 1 minus m2 h hat 2. And Q is 0, so plus 0 for Q, and plus shaft work. Minus P dV dt, of course, but because it's steady state, there's no time derivatives. We assume that the turbine can't expand or anything like that, so the volume is 0 with respect to time as well. All right, and I said Q is equal to 0. So I can solve for shaft work over m dot. So this is exactly what we want to solve for. Work per kilogram produced is shaft work over kilogram. Ws dot over m dot is equal to H, let's see, because I brought this over to the other side, I want to flip the negative sign. So it's going to be H2 minus H hat 1. All right, and I know both conditions of stream 2 and stream 1. So in the steam table, again, appendix A3 in Sandler, for H2, I would look up saturated liquid water at 1 bar. And in the Sandler textbook, it's not written in terms of bar, it's in terms of megapascals. So you have to do that conversion. Quick way to do that is just to divide by 10. So 1 bar is equal to 0.1 megapascals. Another way to remember that is 1 bar is 10 to the 5th pascals, and a megapascal is 10 to the 6th. And then H1 is going to be our superheated steam. And that is at 30 bar, and dividing it by 10 is going to be 3 megapascals, and 550 C. So remember to interpolate when you look up that value in the back of the Sandler textbook, because you only have values for 500 and 600. So go ahead and look those up and calculate what your work per kilogram is. And I went ahead and looked those numbers up. This is what you should have gotten. So 417.5 kilojoules per kilogram for the saturated water, and 3,569.4 for the steam at 30 bar 550 C. You can simply plug those H values, those enthalpies, into the energy balance, and you will obtain the following number for work produced per kilogram: 3,151 kilojoules per kilogram. Seems like a pretty straightforward problem, right? Except there's one critical, huge flaw with this problem. See if you can guess what that flaw is. And unfortunately, with this problem, it's not actually physically possible. In other words, if I put superheated steam at 30 bar and 550 C into a turbine without adding or removing any heat, actually, you would never get saturated liquid water out. So the problem with the energy balance is that it doesn't account for things that are physically impossible. Well, I won't say physically impossible, because It is physically possible, but we'd have to remove some more heat. We'll say a better term for it is that it's not a spontaneous process. If we just simply feed this steam in, we will not get liquid saturated water out. And that is because it violates the second law of thermodynamics. So another example that you can use to illustrate that this principle is that, say I have a beverage that's warm, like iced tea, for instance, and say I add some ice cubes to this iced tea. Or it could be water, could be any beverage that you like that you can add ice cubes to. I think we did a problem like this in MEB one time where I asked you to calculate how cold my water would get if I put it into an insulated jug. When we did that problem, remember, we're assuming that the enthalpy of the ice, the change in enthalpy of the ice, is equal to the change in enthalpy of the water. And back then, we just assumed that the ice would melt. So in other words, the enthalpy of the ice, delta H at ice, is positive, right? It's increasing in enthalpy. And delta H of the water would be negative because it is being cooled. Now, we didn't assume anything different because we know physically that's what happens. If you put ice into something hot, the temperatures will get closer and closer until they equilibrate. But consider this. If I specified instead that the ice actually gets colder, so that delta H ice is negative, and the temperature of the ice is dropping, there's nothing in the energy balance that would break. In other words, if the energy of the ice decreases and gets colder, the energy of the water or whatever is in the drink would have to be getting warmer to offset that. And I could write an energy balance on that, and it's a perfectly valid mathematical equation. The problem is, again, that it's not a physical problem because it's not going to happen spontaneously. So that's all for this video. In the next video, we'll talk about what to do to find whether or not something is possible.